AB Calculus, Section 5.5, Average Value and Properties. Our goals for today are to derive the average value of an integrable function and use it in practice. And our second goal is to state the mean value theorem for integrals and use it also in practice. So a little class opener here. See if you remember these properties from the previous lesson. How does the integral from b to a of f of x relate to the integral from a to b of f of x with respect to x? Well, when we flip these limits, we know that the area beneath the curve for 1 has the opposite sign of the area beneath the curve, or trapped between the curve and the x-axis for the other. Okay, that's a property you need to know. It's going to come up often. Here, when you have the area beneath a curve or trapped between a curve and the x-axis with a width of 0, right? Our lower index or lower limit is equal to our upper limit. Of course, the area will be 0. And you can see that graphically. If I were to sketch f of x here, if I'm looking for the area under the curve from a to a, clearly that has no width, and therefore the area would be 0. Today what we're going to talk about is what's called the average value of a function. And to find the average of any set of numbers, let's take a set of numbers, a0 and a1 and a2, all the way out to the nth term in that set of numbers. What we do, right, is we take the sum of those up to the last term, and we divide by the number of terms. Right, so that would be whatever n terms. So this would be the average, or the mean, or the average value of that set of numbers. Now, if that set of numbers is continuous, right, and you can see it in the form of a function, right? So here's some function. Right, actually, let me sketch that. Let's do it like this. Let's keep it simple. Let's say I've got a function from a0 all the way out to a sub n. All right, and this is a closed interval, right, from a0 to a sub n. Now we're taking on an infinite number of numbers. Right, what I can do is I can find the average value. Right, let's say the average value, I don't know, I'm just gonna make a guess here. Let's say this is 1, let's say it goes up to like 6. Let's say based on the function, the average value ends up being m. I don't know what that is, doesn't matter. Then our function has to take on, assuming that it's continuous, has to take on that value of m somewhere for some value c, right? For some value c, it has to take on that average value. Now, if it's discrete, right, like the example above, right, a0, a1, a2, all that stuff, I should have put a0 in there. I didn't do that. I should have. Okay, let's say it's discrete. Let's say a0, a1, a2, up to a4, right? Let's go from a0, a3. Well, it's possible that the average value is somewhere in between, and therefore, if the function is discrete, right, or if the set of numbers is discrete, meaning that it's not continuous, right, then potentially there is no c value. There is no c value, right, such that a specific term within that set of numbers takes on the average value, right? For example, let's say I do 10 push-ups, and then I do 15 push-ups, and then I do 17 push-ups on 3 consecutive days. And I'm considering this in the hundredths. So this is 10 hundredths, which means 1,000 push-ups. Sorry. So my average, of course, I'd add those 3 up. I'd get 42, and I divide by the number of numbers, which is 3. And so over 3 days, my average number of push-ups would be 1,400. Well, in this case, right, the average doesn't necessarily equal one of my possible outputs for each of those days. So the function needs to be continuous in order for the average value to be attained at any given point in the interval. Okay, so I've gone on a tangent here, no pun intended. But the average value, right, denoted by this f bar thing. F bar is equal to 1 over b minus a times the integral from a to b of f of x dx. Okay, so that's how we're going to calculate our average value of a function. Okay, and we'll talk about an application of this and how we can find this in a much simpler mindset, in a simpler way. Okay, and we'll talk about that in a minute. Okay, so example 1 says a hiking trail has an elevation given by f of x equals this thing. You can see it graphically below, where f is measured in feet above sea level and x represents horizontal distance along the trail in miles from 0 to 5. What is the elevation, average elevation of the trail? Okay, so we could see clearly that it's right about 4,000, right? But we could find the average value of f of x by taking, right, we'll call it f bar, 1 over b minus a, which is 1 over 5 minus 0, times the integral from 0 to 5 of f of x dx. Okay, so really what we're going to do is we're accumulating, right? We're accumulating the area under the curve, and then we're dividing it by 5. So we're taking 1/5 the area beneath the curve from 0 to 5. Okay, and in this case, I'm not going to do the calculation here, but it looks like it comes out to be approximately 4,000. I'm going to confirm off camera with my calculator, and then come back. Okay, so it's not quite 4,000, which you're probably assuming it wasn't based on the graph, but this number right here comes out to be 19,791.67. Okay, so f bar actually, gosh, I keep forgetting to go from highlighter to pen. F bar is 1/5 of this number, and this number is the value that I get here, 19,791.667. Okay, so let's take 1/5 of that, divide that by 5. So yeah, I mean, close enough that on this graph, it comes out to look like 4,000, but it's not. It's 3,958.333. Okay, so that's the average elevation of whatever this trail, hiking trail. Okay, now the point of this isn't necessarily for me to be able to algebraically integrate this expression. The point is to see that you can use the area under the curve to find the average value of the function itself. Okay, so the average velocity, right? The average velocity from 0 to 6 would be, 1/6 of the change in the velocity, which makes sense, right? 1/6 of the change, in velocity, or change in position. So this is the same as 1/6 the change in position. Okay. So if I average my change in position on this given hill, right? And there you go, you got your average elevation. Okay. So let's continue and talk about this thing called the mean value theorem for definite integrals. Okay, mean value theorem for definite integrals. A continuous function always assumes its average value at least once in an interval. Okay, so let's say you're on a hot air balloon ride, right? And you start from, some tower, and your balloon, which looks like this, which is awful. Okay, there you go. And it's floating, and it floats down here, and then up here, and then down here. Okay, and you stop over here at the gym. Got to get in a workout. Okay, but you just drop right on, whatever. Okay, you're not going to the ground. You just tether this thing to the ground. It's still floating. Da da da. Okay, so here's your height. H with respect to t, and this is the gym, but this is the t-axis. Okay, so what the mean value theorem for integrals tells us is that at some point c, right, at some x value or t value c, you're going to reach that average value. So there exists a c such that you hit that average elevation or average value. Okay, so let's just, for the sake of this problem, say that the average value is right here. Well, it looks like there's 3 places or 3 times for which you hit that average value, right? Now, the mean value for integrals says that there's at least 1 point, right? At least 1 point such that that happens, right? Because, travel with regards to height is continuous. You can't, jump from 50 feet off the ground to 10 feet off the ground without traveling through the 40 feet in between. That's all that this mean value theorem for integrals is stating. So using the information from example 1, find the value c such that f of c is equal to the average elevation. Well, we said the average elevation was like 39, what was it? 3958.33. Okay, so what I'm basically doing here is I'm saying I've found the average elevation, 3958.33. I want to find this value c. I'm going to make the assumption that's right around 3. But all that I do is I set that equal to f of x. I use my calculator and I solve. Now, in some cases, you might not be able to use your calculator. In this case, clearly with this kind of number, I would, and the function itself, I would require you to use a calculator because that wouldn't be reasonable. But you can go to your calculator, go to your graph, and I would, in y1, put f of x, and in y2, put your average value, 3958.33. And just find the point of intersection of these two, right? Find that point of intersection, and you got your c value. That would be your c value for which that's true. So I'll come back with an answer in just a moment. Okay, now be strategic, you guys, as you do this. When you do your window on your graph, I went from 0 to 4, I think. Yeah, so I kind of zoomed in on 0 to 4, and I went like 4,500 to 0 to 4,500 for my elevation. And then I saw these 2 graphs show up, right? I saw the actual elevation show up, and it came in blue like that. And I saw my average value show up, and then I just found this point of intersection right here. And that point of intersection happened at x equals, so y1 at 2.917 is equal to y2. Okay, so y1 at 2.97 equals y2, which means that, right, that our function is equal to our average value at x equals 2.917. So there you go. That's our c value for which that's true, using this thing called the mean value theorem for definite integrals. Okay, let's get into a few AP questions here and kind of cruise along. So, example 3. The average value of y equals 1 over x over the interval from 1 to e is the following. So average value, so my average value for f, and in this case, this notation is optional, but you could denote, average value, okay, is going to equal 1 over b minus a, which will be 1 over e minus 1, times the integral of 1 over x from 1 to e with respect to x. Okay, so it's going to be 1 over e minus 1 times, I'm going to integrate, that's going to be the natural log of the absolute value of x evaluated from 1 to e. Now, since both of these values are positive x values, I could drop the absolute value bars right now and it wouldn't make a difference. You want to be careful, make sure that you've got the absolute value and then determine whether or not you need it. So this would be the natural log of e minus the natural log of 1. Natural log of 1 is equal to 0. Natural log of e is equal to 1. So this is really just 1 over e minus 1 times 1 minus 0, which of course will be 1 over e minus 1. So our answer will be e. Okay, let's continue on the next slide. Example 4, calculator allowed the average rate of change of the function f of x over the interval 1 to 3 is nearest to. Okay, so let's talk about this. This is interesting. Now think about this. The average rate of change. So the average rate of change from 1 to 3 would be the same as f of 3 minus f of 1 over 3 minus 1. That's the average rate of change of the function. So that is equivalent to the average value of f prime, right? So that's the average rate of change. The average value of f is different, right? The average value of f is equal to 1 over 3 minus 1 times the integral from 1 to 3 of f of x. I'm not asking for this. This is not what we're asking. We're asking for the average rate of change. So this is what we're seeking. So you don't actually have to use this average value function using integrals. Okay, so let's go ahead and utilize our calculator, because what we want here is f of 3. Well, f of 3 is the integral from 0 to 3 of this thing, 1 plus cosine t squared dt minus f of 1, which is the same thing except from 0 to 1, 1 plus cosine t squared dt over 3 minus 1, which will be 2. So this will be the average rate of change of the function. Okay, so I got to use my calculator clearly. I'm not going to try to do this with your traditional FTC part 1 methods or this. Okay, so I'm going to find those values using my calculator, and then we'll look at the answer. Okay, so I'd like to talk about the answer. So I evaluated the numerator all at once in my calculator. Go back to your pen, not your highlighter. There we go. And I got 1.715 and change, okay? And I divided that by 2, and that gave me this. Now that required me to press math 9, y1, 0 to 3, blah, blah, blah. And then do the same thing, math 9, y1, 0 to 1, dt. Now if you typed into y1, and you pressed math 9, and you went from 0 to x, 1 plus cosine of x squared dx. Okay, if that was y1, then what you could have done in your calculations in your calculator, so type that into y1, as opposed to pressing math 9 on your home screen and having y1 be, so here are your two alternatives, right? You could have y1 be the square root of 1 plus cosine of x squared, and then you could go to your home screen and, you know, press math 9 twice, take the difference, divide by 2, or you could do this, and then on your home screen just do y1 of 3 minus y1 of 1 over 3 minus 1. Both of those are acceptable, and you'd get the same answer. You'd get this 0.858. That was not well written. Let me try that again. 858. Okay, you get it in either case. Now there's just different ways you could go about it. The more you play with your calculator, the better you're going to be at this stuff. Okay, so that's the average rate of change. It's still an average value. It's just the average value of the derivative. So with that being in mind, let's talk about this for a second. Let's say you have x of t. If you want the average position, then you do, on some interval, you do 1 over b minus a, integral of x of t from a to b, dt. This would give you the average position. What if you want the average velocity and you have x of t? Well, if I want the average velocity, recall that the average velocity, or the slope of the secant line, right, is equal to x of b minus x of a over b minus a. So you may not, if you're trying to find the average velocity and you're given the position, you may not have to use integrals at all, depending on what function you're working with. Okay, that's a special little nugget of information. Kind of keep that in your back pocket. Okay. All right, let's look at the next example. Example 20 from 1997. Okay, average value of cosine in the interval from -3 to 5. Okay, so now I'm looking average value, not average rate of change. So this is going to be the average value of cosine. Let's set f of x equal to cosine x. Thus, f bar will be equal to 1 over 5 minus -3. So the interval length is 8 units. We're going to go from -3 to 5 of cosine of x dx. Okay, so our average value will be 1/8. Okay, I'm going to hesitate to eliminate answers based on this 1/8 piece, right? because potentially there could be a reduction of something, so potentially we could reduce to something over 2, but we'll just be real careful. Okay, and we're going to integrate cosine, which is sine evaluated from -3 to 5. So what we would get for our average value is 1/8 of the sine of 5 minus the sine of -3. Now, we got to be real careful here, real careful. I don't see that answer in my potential options over here. Sine of x is an odd function. Remember, an odd function, f of -x is equal to -f of x. Thus, sine of -3 is equal to negative sine of 3. Therefore, this actually is equal to 1/8. This is a nice little example. Okay, this would be sine of 5 minus a negative sine of 3, using that property of odd functions. Thus, this would be the average value. Nice little twist in this problem would be 1/8 the sine of 5 plus the sine of 3. Let's find that. In our options, it looks like that option is E. Okay, so again, nice little nugget of information right there. Let's continue on the next slide. Okay, Calc Aloud 2003, number 83. Velocity in feet per second of a particle moving along the x-axis is given by v of t is that. What is the average velocity of the particle from 0 to 3? So I'm given velocity, asked for the average velocity. Thus, the average velocity, v bar, is going to be 1 over 3 minus 0, which is the interval given, integral from 0 to 3 of v of t, which is e to the t plus t e to the t. Okay, when you look at that, the integral should seem complicated to you, which is hence why calculator is allowed. So what I'm going to do for v bar is take 1/3 of whatever this value comes out to be in blue here. Okay, e to the t plus t e to the t dt. Okay, so I'm going to go off camera with my calculator, come back with an answer. Okay, I'm back. My calculator gave me an answer. I'm going to get 1/3 of the following. I had 60. Now, I don't want to round in an intermediate step, so I don't want to round now and then use this number to then divide by 3, because then I'd be technically rounding twice and potentially off far enough that my answer would not be correct. This is my calculator's answer, but I would take that number, divide by 3. It gives me 20.0855, which of course lines up well here with part A. Now, if you've got more steps to go, which we will later on in the chapter, I would store this using stow so that you don't have any rounding issues down the line. Okay? All right, let's look at 04, Form B, number 3D. This is calculator allowed. Okay, we're just going to look at parts C and D. Apparently A and B don't apply to this section. So a test plane flies in a straight line with positive velocity, v of t, in miles per minute at time t minutes, where v is differentiable function. Selected values of v of t over the interval 0 to 40, which is in minutes, are shown above. The function f is given by f of t equals 6 plus cosine of t over 10 plus 3 sinus 7t over 40. This is used to model the velocity of the plane in miles per minute for 0 to 40. According to this model, what is the acceleration of the plane at t equals 23? Indicate units of measure. Okay, so f of t is used to model the velocity of the plane in miles per minute on that interval. So if we want the acceleration, so if v of t is equivalent, I shouldn't say that. Let me start over again. F of t models the velocity, then f prime of t should be equal to the acceleration at time t. Okay, so according to this model, right, this model, not the table above, what is the acceleration of the plane at time t equals 23? That means what I want to do, and of course this is calculator allowed, so I'm gonna plug f of t equals this in for y1. All right, so I'm going to take and find f prime at 23 by doing the following. I'm going to plug in for y1 my function 6 plus cosine of t over 10 plus 3 sine of 7t over 40. And what I'm going to do is I'm going to find y1 prime at 23 using my math9 function on my calculator. I'll come back with an answer in just a moment. I think I might have said I was going to use my math9 function. I'm actually using math8 to go from any function to its derivative. You use math8. And when I do that, the acceleration of the test plane at time t equals 23 minutes ends up being negative 0.408. Now units, let's talk about this. This is going to be miles per minute per minute. Okay. All right, let's look at part D. According to the model F, given in part C, what is the average velocity of the plane in miles per minute over the time interval 0 to 40? Okay, so apparently I'm not going to use this table at all. That must have been used in parts A and B. So I don't need to use the table at all here. So I'm just going to go ahead and scroll down. According to the model, what is the average velocity? Okay, so f of t models velocity. Therefore, average velocity, okay, is going to be f bar. All right, f bar is going to be 1 over 40 minus 0, which is 1 over 40. Integral 0 to 40 of f of t dt. Okay, so I've already got f of t in my calculator as y1. Now I'm going to use my math9 function on my calculator. So I go math9, 0 to 40, y1 with respect to x. I get a value. Don't forget to then multiply by 1/40 or divide by 40. And it looks like the average velocity, f bar, which is the average velocity of the plane based on the model F okay, I just put that there to kind of note what F bar really means. Ends up equaling 5.916 miles per minute. Okay, that's it for that example. We got one more slide. Let's get to it. Yes, 2013, the coffee maker. Let's do it. Non-calculator, so you can toss that TI to the side. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in a cup for, what does that end up being, 6 minutes from 0 to 6 is given by a differentiable function c. That is the amount of coffee. Selected values of c of t, measured in ounces, are given in the table above. So that means 1 minute after the coffee maker starts, there's 5.3 ounces of coffee in the coffee maker. Then at time 2, 8.8, time 3, 11.2, time 4, 12.8, times 5, 13.8, etc. Using the data in the table, approximate C prime at 3.5. Okay, so approximating C prime at 3.5. So that's an approximate change in ounces, right? So what I could do, and what would make the most sense, is to take the average rate of change from 3 to 4. So I'm going to take C of 4, so C prime at 3.5 is equal to, actually I should say approximately equal to, C at 4 minus C at 3 over 4 minus 3. It's just the average rate of change of the number of ounces of coffee in the mug or in the cup or whatever this thing is from time 3 to 4. Okay, so that'd be 12.8. So that would be approximately equal to 12.8 minus 11.2 over 1. So C prime at 3.5 is going to be approximately equal to 1.6 ounces. Don't forget your units. Does it ask for units? Yes, it does. Units of measure would be ounces per minute. Okay, perfect. B, is there a time between 2 and 4 at which C prime equals 2? Justify your answer. Okay, so this is screaming mean value theorem. This is going back, right? This is saying show that there's a time, or is there a time in this case, where the change in the number of ounces is equal to 2 within that time interval. Okay, so with mean value theorem, the first thing we want to start with is to be able to say that C of t is continuous on a closed interval, 2 to 4, and differentiable, I'm not going to write it all out, on the open interval, 2 to 4. Now let's look at the problem above, okay, where it talks about the initial parts here. C is differentiable from 0 to 6. Thus, if C is differentiable from 0 to 6, it's got to be differentiable from 2 to 4. And if a function is differentiable, then it has to be continuous, right? Therefore, both of these would check. Now, the second thing we want to do is we want to calculate the slope of the secant line, okay, which is the average rate of change of C of t from 2 to 4. So we're going to calculate C of 4 minus C of 2 over 4 minus 2. Let's do a quick calculation on that. C of 4 is 12.8. C of 2 is 8.8. And 4 minus 2 is 2. Thus, this is equal to 4 over 2, which is equal to 2. Okay, and our third part is we're going to make a statement. Therefore, by the mean value theorem, you have to state this. This is 1 point right there. There exists a t where t is between 2 and 4 such that C prime of t is equal to 2. Okay, so because the slope of the secant line, okay, from 2 to 4 equals 2, that guarantees by the mean value theorem that there is a t value between 2 and 4 such that C prime at t is equal to 2. All right, let's move on to part C. Use the midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value, or the, in this case, this is asking for the average value of C of t over that interval. That means the average amount of coffee in ounces during that time frame. So we're going to use a midpoint sum with 3 subintervals. So let's talk about those 3 subintervals. The first interval would probably be from 0 to 2, second interval from 2 to 4, third interval from 4 to 6. Now I'm going to highlight a few values here. I'm going to highlight the values that are in the midpoint of each of those intervals. And those values are going to be utilized here in just a moment. Okay, so for part C, 1/6 of the integral from 0 to 6 of C of t. We're going to use the midpoint method to approximate this integral, okay? And then we're going to multiply it by 1/6. Okay, so let's do that. So the midpoint, when we talk about a rectangular method using midpoint, we take the width of the interval. So the first interval is 2 minus 0 times C of 1 plus the next interval. It'll still have the same width because all these intervals have the same width, or width of 2, but I want to isolate how we're getting those 2's. Okay, and then we're going to take it by the times the height of the output of the midpoint of the interval. Lots going on there. So that'd be C of 3 plus 6 minus 4 times C of 5. So notice how each of these intervals, right, 0 to 2, midpoint is 1. 2 to 4, midpoint is 3. 4 to 6, midpoint is 5. What we're going to do is we're approximating the average amount of coffee in the mug during that time frame. Okay, so I just got to do a little bit of work here. This is no calculator, I believe, so I got to do some math. Let's do it. So this will be 1/6. And of course, I should, like a good mathematician, I should make this an approximation, right? Because the highlighted pieces are not equal, right? The highlighted piece on the right with all these widths and heights, that's an approximation of the actual integral. Okay, so this would be 2 times 5.3. 2 times 5.3 is 10.6. Okay, and then 2 times 11.2. 2 times 11.2 is 22.4. Plus 2 times 13.8. That'll be 27.6. I think. 13.8, 27.6. Yeah, that works out. Okay, so what do we come out to get? All right, so we get 1/6 of, that's going to be 32, it's 33, 33, and 27 is 60, so we get 60.6 for that summation. All right, so this is going to be 1/6 of 60.6. Well, 1/6 of 60 is 10. 1/6 of 0.6 is 0.1. So the average amount of coffee in the cup from time 0 to 6 is going to be that many ounces. Okay, part D, the amount of coffee in the cup is modeled by this function. Using this model, find the rate at which the amount of coffee in the cup is changing. Okay, the rate at which the amount of coffee is changing. So if this models the amount of coffee in the cup, the rate at which the coffee is increasing or decreasing would be found by using B prime. So I'm going to enter B of t in for y1 into my calculator, or do I not have that ability? Is this no calc? Of course, this is no calc, so I got to do a little manual work here. Okay, so I'm going to scroll down here, work part D. This will be the end of our lesson here in just a moment. Okay, so B of t is equal to 16 minus 16 e to the negative 0.4t. I see some chain rule coming to us. The rate of change is the coffee, the amount of coffee in the cup is going to be modeled by B prime of t. Okay, so the derivative of 16 is 0. The derivative of negative 16 e to the negative 0.4t is going to be negative 0.4 times negative 16 e to the negative 0.4t. Right, I use the chain rule to work through that. Okay, so B prime of t is going to be, okay, it'll be positive 1/10, or 0.1 of 16 is 1.6. 1.6 times 4 is going to equal 3.2 times 2, which is 6.4. Okay, so I'm going to get 6.4 e to the negative 0.4t. Now what I want is I want to know B prime at 5, right? It's asking for the rate. Oops, I want a 5 in there. I get talking and I forget to write what I'm supposed to. Okay, I want the rate at which the amount of cup of coffee is changing when t equals 5. Okay, so that's going to be 6.4 e to the negative 0.4 times 5, which will be e to the negative 2. So negative 0.4 times 5 is negative 2. Okay, so you could leave your answer just like that. And this would be ounces, ouch, not ouches, ounces per minute. Okay, or you could rewrite it as, 6.4 over e squared ounces per minute. All right, let me make sure my units are right here. This is just me being thorough. You should do the same. Yep, units are right. And that's it, guys. I hope this stuff makes sense. That's average value. So we'll see you in the next video. Have a great day.